Hello everyone, thank you all for watching. My name's Stuart and I'm here to talk to you about the software engineering that drives our use of stricter typing. Now where does this talk come from? Hopefully many of you were at PHP Southwest back in January, and if you were, you'd have seen two great talks by Rob Allen and Dave Lidderment looking at the static analysis tools that the PHP community has built for helping you use types in your code. Now afterwards, Dave and I went and had a long chat in the pub. Sorry, Dave, because I felt very passionately there was more to say about this. If you're going to use these tools, I think it would really help if you knew how to actually use stricter types and why they work the way they do. And that's where this talk came from. If you're not primarily a PHP programmer, don't worry. Yes, the examples are in PHP. The software engineering is not. You can use the software engineering principles I'm covering in this talk in your language of choice. So let's get into it. And let's start by defining the problem. What is the problem we're trying to solve here? I'm a big fan of using a worked example to do that. So I had to think about this, and I've come up with an example, and all it does is calculate sales tax, sometimes known as VAT, depending where you are in the world. That's all it does. And here it is. It takes two inputs. It takes the amount of money we want to tax. It takes the tax rate to apply. It uses a simple percentage to work out how much money is owed. And for context, imagine this as part of some sort of shopping cart of some kind. Now, I can't see you, but hopefully many of you are looking at this and you're shaking your heads. Hopefully many of you have started to see problems with this code. And we can sum those problems up using two terms. First of all, our function is not robust. We can pass garbage into it. We can pass strings to it. We can pass, nulls. We can pass objects. Hell, we can even pass file handles to it right now. Things that the code can't cope with. It's not robust. And hopefully you've spotted the code's not correct either. There are circumstances where it's going to produce an invalid result, even if we give it, even if we don't pass garbage into it, we're still going to get some bad outputs. These are things we want to fix. So back to our example code. As programmers, we can say that the input amount and our tax rate are going to be numbers of some kind. We might disagree about the kind of numbers, but we can say they're going to be numbers. Some languages can work that out as well using a process known as type inference. PHP can't. So the normal starting point for cleaning this up would be to add some check tests, some input validation, some preconditions, some assertions. And they might look like this. We might make sure our input, our amount of money to tax, is an integer. And if we're doing it for one, we've got to do it for both. So we'd make sure that our tax rate was also an integer. So at least they were consistent. And we'd have separate tests, separate preconditions for each of these so that we could throw different errors. So if we had a bad input, we'd know which one was going on. Many of us have written code like this. Some of us have probably written this exact code. But hopefully you can see that our code's starting to balloon. We've gone from this to this. We've gone from one line of executable code to 5 lines of executable code. And that's just for one precondition. There's many more we've got to add to make this code work well. So we can draw some conclusions from this. If we're not using type hints, we're writing these preconditions. Someone's got to write them. Every single one of these checks has to be written. All this input validation has got to be written by someone, and that takes time. Not only does it take time to write, it takes time to run. Every time the functional method's called, these checks have to be executed, every single time. The computer has no way of knowing whether the code has already been checked. you're in a bad situation there. And let's not forget the testing burden. There's absolutely no point in creating all these tests and all these input validation, adding them to your code, if you're not also making sure they're covered by unit tests, if you're not making sure they work. So we've increased the amount of code we've got to write, we've increased the amount of code we've got to run, and we've increased the testing burden. It's no wonder people don't do this, especially when you look at where we are today. The time it takes us as developers to do our jobs is often the biggest bottleneck on a project and often the biggest cost. We want to be able to ship software quicker. And that's where type hinting comes in. You can indeed use type hinting to replace some of these runtime checks, especially these kind of runtime checks. These tests for integers, we can take them out of our code and move them into the function signature and make it the language's problem. And now our business logic doesn't have to worry about it. It's got two integers, it will calculate a percentage. What's the problem? Well, hopefully you can see that we've not solved our problems. Although it might look like it, we can still pass garbage into our function. And because we can still pass garbage into our function will still output values, results that aren't always correct. So here's 4 examples off the top of my head when I was writing this talk that I came up with. I wouldn't be surprised if you're looking at the code and you've spotted some more that I haven't. Why is that? We've made them integers. Why hasn't that made things safe? Why have we still got problems? Well, the thing is with an integer is it's too big a data type. We made our amount of money to tax and our tax rate integers because they map onto integers. But it doesn't work the other way around. Not every integer is an amount of money that we want to calculate VAT for or sales tax for. There are integers that are invalid values of the amount of money to tax, I promise you, and we'll show you that later on. And certainly, most integers aren't valid tax rates. So we've still got a problem. Integers aren't strict enough. So let's talk about this from a software engineering point of view. What is this input validation? Well, it's something we call defensive programming. Hopefully you've heard the term before. And the whole idea of defensive programming is we want to make sure our business logic is only getting data that it can cope with. So we're adding runtime checks to do input validation. That's what we're doing. And that's what defensive programming is. You may have heard of the term design by contract. Now this goes a bit further, and you could say it's much more of a century type approach. Because with design by contract, what you're also doing is you're checking return values before you send them out. So if you've got a piece of business logic that produces a bad return value, it's caught immediately and doesn't propagate throughout your code. You're not propagating error data throughout your code, which is a good thing to do. Good thing to catch these problems. However, as we've already demonstrated, there's a big problem with this. Your business logic's at the back of the queue to be run. Inputs have to be validated first, and your business logic has to wait. Then it runs. Then everything's got to wait while your output is validated. And then that might go into another function where, again, your inputs are being validated before your business logic runs. Effectively, your business logic is stuck in a queue behind all this other code to run. So what we can say is we can say that code that relies on runtime checks is slower to write because someone's got to write all those checks, and it's slower to run because the computer's got to run them. It's no wonder people don't practice defensive programming. That causes other problems. The thing is with defensive programming is it's only effective if you're very good at doing it consistently, if it's everywhere. If you take a project with, say, 5 developers, and let's say 2 of them practice defensive programming, that means 3 others are adding code that's not robust and isn't guaranteed to be correct. You're shipping potential bugs. You have to, if you're going to do defensive programming or design by contract, you've got to do it everywhere. Now, there's another reason I mentioned design by contract. It's an old technique that came out of research into the emerging field of object-oriented programming. Even back in the mid-80s, people could see the problems we were going to have if we adopted OO en masse, and by and large they've been proved right. So what am I on about here? The problem we've got is how OO is meant to be used versus our code today. So the idea with OO was you were meant to interact with something based entirely on its behaviours. You weren't supposed to see its state. You weren't supposed to care about its state. You weren't supposed to care about the data inside. And that's not what's happened. Our code today is all about data. That is the prevailing programming style today, and we just use OO as a way of organising our code. But what if we could go back to that original promise of object-oriented programming? What if we could use it to prevent plugging incompatible data into our business logic? Just like I can't take a British plug and plug it into the wall in America. Our electrical mains systems are incompatible, so the plugs are incompatible. What if we could do that in software terms? What if we could take our function and use strict types to prevent us plugging bagged data into our business logic? That's what we're going to talk about. We're going to talk about using our type systems to make bad data a bad fit. Hello everyone, and welcome back to part 2 of my talk about the software engineering that drives our use of stricter types. Hello. Right, so in part 1 I set out the problem. We looked at an example piece of code and we looked at how you might start to use defensive programming to make the code more robust and correct. We also looked at the problems with defensive programming and how you can't just use PHP's standard type hinting to slap on a couple of types to solve those problems. So what I want to do now, there we go, back to the slides. In part 2, I want to look at how you go about using stricter typing, and it all being driven by the software engineering. There's 2 outcomes we want. We want to make our code robust and correct, and we want stricter types to help us achieve that. So our starting point is a process known as type refinement. Here's our example code again. And what we're going to do is we're going to start off by focusing on our 2 inputs. Just to remind everybody, amount is the amount of money to be taxed, and rate is our tax rate to apply. And I want you to imagine some context here. This shopping cart, this is part of a shopping cart. Okay? Now what we can say about those 2 inputs is that they are values. And to make sure we have a common understanding, a value is data that has no identity. Now what does that mean? It's to do with how we compare 2 values to see if they're the same or not. The equality operator. If we have to look at all the pieces of data that makes up the value, and if we have to compare those against all the pieces of data that makes up another value, they don't have identity, and therefore they are values. The flip side of this is something known as an entity. which you may have come across from working with databases. And something's an entity if you only compare some of the pieces of data that makes up your entity. For example, you're comparing primary keys to see if two things are the same. That's what makes something an entity. There's an argument to be made, and a very strong one, that our tax rate is actually an entity, that it has an identity. For the purposes of this talk, I'm going to treat them as values. I didn't want to confuse people by using the term values and entities throughout the talk. And the differences between values and entities actually aren't important for this talk. Everything I describe here about values applies equally to entities. So let's look at the two types I'm introducing. Our amount to tax and our tax rate. What can we say about those? Well, we can say that those are value types. Now, you might have heard the term value objects, and the reason for that is in some languages, and PHP is one of them, there isn't a richly developed type system. They're OO languages primarily, and therefore you have to use the OO tools, classes and objects, in order to do stricter types. So already our way forward is being set for us. We need to create a class for each of our two types. And because they're values that need to be initialized, each of these classes needs a constructor. So these constructors are going to need some parameters. And that guides us forward for our next question, is what do we need to know to create these values? What input parameters do we need? Now, a good place to start is with the types we're replacing. Originally, we were going to use integers for our two values. So we can start with those. Our amount to tax, we can say, well, it takes in an amount that's an integer. Fair enough. Not much, that's quite easy and quite straightforward. For our tax rate, we can do the same thing. We can say our tax rate's an integer. Again, very simple, very straightforward. Now, you may have noticed I've actually added two parameters to our tax rate type. And that's because I'm preempting the next question we have to answer, which is to look at the work that these constructors are going to do. Now, why do they need to do any work at all? Well, the whole reason we're creating these stricter types comes back to this statement that we said in part 1. Integers are too wide a data type. We can't accept every integer. We have to refine them. That's what type refinement is. We take in a wider data type, we do some input validation, so what comes out the other end is a narrower data type, like our tax rate. That's all that type refinement is. And we say that the work of type refinement is done by something we call a smart constructor. That's what these constructors on our value types are. They're smart constructors. So let's get into smart constructors. And let's return to our question, is what work are these constructors going to do? Now, what they're going to do is they're going to enforce the data constraints that apply to our data type. To make sure we have a common understanding, all a constraint is a condition that you have to meet. You can't work around it, you can't pretend it doesn't exist. It's something you have to incorporate into your design, and therefore into your code. Anyone who's done any sort of software design, technical architecture work, infrastructure work, business analysis work is probably familiar with the term design constraint. Same idea, just applied to data. So what are the constraints for our data types? What's the constraint for our amount to tax? Or to put it another way, what are the preconditions that must be met? How do we need to validate our input? Now, for our amount to tax, it's part of a shopping cart. So I've decided that there's a constraint here which we're not going to accept negative amounts of money. Otherwise, we could just use integers. It's a shopping cart. We might give some goods away for free, but in general, customers are meant to pay us for the goods we're selling. So negative amounts of money are an error condition that should never reach our code. So we're going to check for that and throw an error if it occurs. For our tax rate, the input validation is going to be more complex. There's a chance, for example, we've actually got to go and look this up in a database or in a config file of some kind. It may not be something we enforce entirely through an algorithm. So anytime we have more complex input validation, it's very normal to move that into a separate function and call it from your constructor. This is a style of programming you're probably already doing. It's very normal. And that's it. That's all smart constructors do. So what we can say about smart constructors is that their job is to prevent creating illegal values. That's how you decide whether your smart constructor works or not. Now, I can't see you, but I imagine if we were in a live audience, some of you would be shaking your head. Because doesn't this look like defensive programming? I'm talking about input validation. I'm talking about preconditions, the same terms I used when we talked about defensive programming and design by contract. Isn't this just the same, and aren't we just adding more of it? Well, not quite. There's a thing about smart constructors. Their output, these value objects that we're creating, they're guaranteed to be legal. That means you can trust them elsewhere in your code. You don't have to do input validation elsewhere in your code if you're consuming stricter types created by smart constructors. Now this has the effect of moving defensive programming from literally everywhere to where we are creating this type data. That's what we're doing. So we're massively narrowing the surface area where we need to use the technique of defensive programming. That's the benefit of smart constructors. And we can go a little bit further to narrow it even more. And to do that, we're going to look at something called data guards. Let's go back to our tax rate example. And I mentioned this style of programming where the input validation is actually moved off into another function or method. I mentioned that's very normal. Now imagine that function or method looks something like this. It takes a bunch of inputs, it inspects them, looks at our, does it meet our data constraint? And if it does, it returns true. If it doesn't, it returns false. Any function that follows this pattern, we can call it a data guard. It returns true if a data constraint has been met. That's what it does. To make these more reusable, we make sure that data guard only checks one data constraint. And only one. And that allows us to build more complicated scenarios from our pool of data guards. If you need a term to describe these more complicated scenarios, you can call them a specification. And you can think of that as just being a data guard that just calls other data guards. A specification might be, for example, an Amazon Prime customer. That's someone who's a customer, who's an Amazon Prime subscriber, and that may entitle them, in your business logic, to additional benefits. That's an example of a specification. Now, the other thing about data guards, It's not their job to throw errors. At all. They don't report any kind of errors. They just say yes or no. If you want to throw exceptions, that's the job of a data guarantee. Let's go back to our example code again. Now, as it's written at the minute, it's our smart constructor's job to work out if an exception needs to be thrown or not. Thing is, with that style of programming, who does that? Who reliably looks at the return values from functions and methods to check for error conditions? And who does it all the time? I can tell you from 25 plus years of experience in this industry is that if you want to write robust code, it's a programming style you want to eliminate from your code. Don't rely on developers checking return values for errors. Eliminate it from your programming style. Do something like this instead, where all you're doing is calling a function, and if the function returns at all, you know you're safe. It's hard to go wrong with this style of programming. Much harder to go wrong. And this function, it would look something like this. The first thing it does is call our data guard. This is important. Our data guarantees are built from data guards. We don't have bespoke checks in here. The reason for that is our data guards already have, hopefully, good unit test suites. And we don't want to repeat those unit tests in our data guarantees. We don't want to increase our test burden. We identified the test burden as one of the problems of defensive programming, so we want to minimize that. So to do that, we make sure we don't repeat the input validation, the work that the data guard is doing. Don't repeat it in your data guarantee. Call your existing data guard. Therefore, you don't have to repeat all those unit tests. If the check passes, that's great. If the data constraint is met, that's great. If not, the data guarantee throws an exception. That's the value it adds. Its job is to throw those exceptions so that your code doesn't have to. That's a data guarantee. That's all there is to it. Now, you may have noticed I changed style as I was going through that code. I started off with methods on an object, and then they became functions as I went through. Why did I do that? And what's the right way to do this? And the answer is, it depends. At their heart, data guards and data guarantees are an example of a style of programming known as modular programming. The thing with pure OOP, pure object-oriented programming, is you're meant to be interacting with the behaviors of an object. That's where it came from originally. Data guards and data guarantees aren't really part of an object because you're not interacting with the object state, because you're calling them before the object has finished being created. So they kind of live in this grey area. So you may prefer to create them as functions inside a namespace, and you may find that that's more reusable over time as well. There's another question that our examples are throwing up. Some of you in the audience might be sat there wondering, why have I given it such this weird name? It's an amount to tax and it's somehow related to a shopping cart. Why didn't I go with something more generic, like currency or money? Yep, why didn't I do that? Well, we're now ready to talk about robustness. So let's go back to our example function. And let's focus in on this type here. Excuse me. And actually, let's go a bit further than that. Let's actually replace it with money. That looks nice. You can see the attraction of that. It's very easy for someone to read that and know what they've got to provide. But here's the question. What about the data constraints? Is money identical to our amount to tax for a shopping cart? Are the data constraints the same? Well, we go back to this point that we made in part 1 and we've already returned to once in part 2. We're going back to it again. And instead of integers, we can replace those with money. It's absolutely the case that the amount of money to tax is always money. Absolutely the case. But here's the thing. Not every money is an amount we want to tax for our shopping cart. The context matters. Because we've got that constraint about not accepting negative amounts of money. So what we're doing here is we're making stricter types to make our code more robust. That's what we're doing. But you can't just use any old stricter type. You've got to use a type that's strict enough. See, what robustness is, it's about how well your code prevents invalid input coming in. That's what robustness is. Code is robust if no invalid input can get through. Your robust code is actively preventing bad inputs reaching your business logic. It's protecting your business logic so that your business logic can work with data it can trust. That's what robust code is doing. And if you're using stricter types to do this, you're going to end up with stricter types that reflect your problem domain's language or jargon. That's what they're doing. So in our case, we've got our cart amount to tax, because this is part of a shopping cart. The problem here isn't the type we're using. The problem's actually our function name. Validate that is too generic. From the function name, you've no idea what the context is, and therefore you can't see why the stricter type makes sense. One way to solve that, if you're using functions, is to add the context to the function name. An alternative, which is just as valid, is to actually put this inside a shopping cart class of some kind. And now inside those contexts, things start to make a lot more sense. So we originally had this statement, but our function wasn't robust and wasn't always correct. It's now robust. We've created stricter types that if they do their job right, our business logic is getting data it can trust. But what about correctness? Let's tackle that now. What do we mean? So to talk about correctness, we need to focus in on the actual business logic, the algorithm that's going on here, which is our calculation of the amount of money owed. And the question is that calculation the right one all the time? I don't know. It works for my jurisdiction. Does it work for yours? I can't tell you. But here's the thing. We've got this tax rate object being passed in. So why don't we make it do the calculation for us? Why don't we take our business logic and replace it with this, where our tax rate knows how to do the calculation. If we do that, then our code is robust and correct. Now, what I'm trying to illustrate here is an important point. I've heard people say you don't need to write unit tests because you can use stricter types instead, and that makes me tear my hair out. There's no two ways about it. Stricter types don't guarantee your code's correct by themselves. That's not what they do. But what they are is an opportunity. We can treat some of our stricter types as a form of plugin and use those to send the correct behavior into our business logic. Now, I keep talking about correctness, so let's give a definition to finish up on that. Code is correct if, for one given legal input, it always produces the same legal output. That's correctness. That's all correctness means. Good value in, you get the right value out each and every time. And it does mean that correct code has another property. It's always deterministic. And that's a topic for another talk as well. So that concludes part 2 of our talk on how to use stricter types.
Okay, so that's part 2 done. We have a question from the audience. The question from Dan is, what features could PHP steal from other languages to make this easier to do in PHP?
Okay, so first of all, is my audio working?
It is, yes.
Awesome. Dan, that's an excellent question. The first feature it could steal would be type inference. Functional languages and TypeScript to a certain extent do this. And that's where the language itself at compile time, which admittedly PHP doesn't have a compile phase in the same way as some other languages do. But what it's doing there is it's enforcing types by looking at how a variable is used and working out what type it's likely to be as a result. That would be a really big one. Another feature that PHP could steal from other languages is something known as branded or flavored types. One of the problems of using value objects everywhere is the performance hit you take. Objects are slower than primitive types, and quite a lot slower, unfortunately. So if you write a PHP code with heavy types everywhere, and you end up creating a lot of objects all the way through, you're really hurting your code performance simply from the amount of objects you're creating, unfortunately. Now, branded and flavored types, this is a TypeScript trick more than anything else. At runtime, they resolve down to like strings and integers as normal. All the object side of it disappears. But at compile time, they've actually got more type information available due to the very unusual way that interfaces work in TypeScript. So you can, for example, use that to say that this measurement's in feet and this other measurement's in meters. So you don't try and add the wrong things together and blow up space rockets and things like that. So those are two big features. Generics don't help either way. They certainly don't help with this kind of thing. Generics solve a different kind of problem. Does that answer your question, Dan?
Hopefully he'll put in chat if it does or doesn't. And if he's got a follow-up, then please follow it up. We have another question from Doug. Can or should a data guarantee call multiple data guards? And should it throw multiple exceptions?
That's a very good question. In my opinion, I always write them a one-to-one relationship, one data guarantee for one data guard, and I'll make the data guard more complicated most of the time. I find where I've been using this technique, if something's been rejected, I don't really care why, because it either fits or it doesn't, and if it doesn't fit, it's normally obvious from looking at the data as to why. But there's no reason you can't actually have a data guarantee called multiple data guards if you want, if you prefer that as a style, if you find that easier to, for example, debug your code or test it. Just hasn't been my experience. Does that answer your question, Doug?
He can let us know. I think we have a follow-up from Dan, actually. Oh no, Doug's saying yes, thanks in chat.
Awesome.
And now Dan has said, if all correct code is deterministic, how does that work across network calls which might fail? Or is this what you're about to go on to?
No, I'm not about to go on to that. The third part is just a summary of what we've already covered. There's nothing new in the third and final part. Network calls being that is a very good question. Network calls can't be deterministic by their nature because they're talking to an external system. So that means you can't guarantee the code's always correct, so you can't always trust it.
Okay. Dan has said, thank you. I've also got a question, if I may. It's about, you mentioned unit testing. So you can unit test your data guards individually, but then you wouldn't necessarily want to replicate the same tests again. So suppose in your VAT example, you had 2 data guards for the rate and the amount. Presumably, you'd have to test you still want tests for the constructor to make sure if you passed in non-valid values, the data guards are being called.
Yes, you do. What I do with that is I put the tests for the data guards into fixtures, and then I'll pass them in as a data set to loop over. So the unit test ends up being like 3 or 4 lines of code, and they're sharing the same input data with the underlying data guards. And that's how I keep the test burden right down.
Brilliant. Well, thank you very much. Yeah, I think I might try that.
Please do.
Hello everyone, and welcome back to the third and final part of my talk about the software engineering that drives our use of stricter typing. And what I'm going to do in part 3 is we're just going to summarize everything we've said in parts 1 and 2. So, the problem we're dealing with is if you've got runtime checks in your code in order to make your code robust and correct, those runtime checks make everything slower. It's slower to write and it's slower to run. That's a problem in today's world where software developers and how long it takes us to create and ship our code is often the biggest cost and the biggest bottleneck. So we looked at how we can use stricter types to solve this problem. And the general idea is we don't abandon defensive programming. We just move it from absolutely everywhere to the places where we create our data. So we reduce the amount of code that needs defensive programming added. We start off with a process called type refinement, where we start to take inputs from more generic types like integers, apply input validation so that what we get out of it is a smaller data type like a tax rate. This is done by functions and methods called smart constructors. And it's their job is to prevent illegal values from being created. Smart constructors call functions called data guards. And their job is to enforce data constraints. They inspect the input and return true if the constraint's been met. To make your code easier to maintain and to make it possible to reuse the data guards so that we shrink down the surface area of our defensive programming even more, we make sure each data guard only checks one data constraint. And if you've got data guards that are built from other data guards, for example, an Amazon Prime customer, as someone who's a customer and is an Amazon Prime subscriber, we call that a specification. Now, it's not the job of data guards to detect errors and throw exceptions at all. But that's something that we've got to tackle because we can't rely on developers looking at return values of functions and methods to check for errors. It's not a reliable thing. If you want to make your code robust, it's a programming style you need to eliminate. So we use something called data guarantees. And their job is to throw an exception if a constraint's not been met. Now, to make sure that we're not repeating ourselves, our guarantees don't create new tests. All they do is they call data guards. And that way we don't have to create lots of extra unit tests in order to check our data. And what this is leading to is stricter data types that improve the robustness of our code, but only if we get the right amount of strictness. And so we end up with a situation where our type names reflect the problem domain where we're programming within or designing within. And our example was our amount of money to calculate sales tax for. We didn't call it money. We called it CartAmountToTax because it was stricter than money. There were circumstances where money would have values that we didn't want to accept in our shopping cart. I want to pour cold water on the idea that if you're using stricter typing, you don't need tests. It's not true. Stricter tests aren't enough to guarantee your code's correct. You've got to go further than that. But what they are, they're an opportunity for us to deliver the correct behaviour into our business logic. We can go back to how objects were originally meant to be. And we can attach behaviour to those types so our business logic can call them. And we gave the example of calculating tax for each jurisdiction. I don't know if the rules are different where you are to where I am, but if those rules are attached to the tax rate and we have a tax rate object for each jurisdiction, then our business logic doesn't care. It simply calls the plugin and it's the plugin's problem. So thank you for watching our talk. If we can help you move to stricter typing, if you need any help with that, please get in touch. Thank you.
Well, thanks very much, Stuart, for that excellent talk. Has anyone got any questions? If they do, please can you pop them into the Q&A? Okay, so we've got a question from John. It says, "Hi Stu, I haven't heard of the terms smart constructor, data guarantee or data guard. Where do they come from? A particular book or language or paradigm? I assume you didn't make them up."
Hi, John. That's a very good question. Smart constructors is a term used a lot in functional programming, I believe. I think that's where I came across it. Data guards and data guarantees, they are my own terms. They're an extension of similar kinds of terms you find in the TypeScript community, for example, where they have a type of function called a type guard, which is used to help the TypeScript compiler work out what type of data you're looking at compile time to help it decide whether or not the code is allowed to compile or not. That's it.
Cool, thank you. So if you have any follow-up on that, John, then just pop it in Slack or pop it in chat or the Q&A. I did actually have one further question. Oh yeah, no, John's happy with the answer. Thank you, thank you. Another question from Dan. What are your thoughts about the recently declined operator overloading, and does it relate to the problems presented in your talk? So this is the user operator overloading RFC.
I think what we can do with that is we can look at what's happened in the C++ world, which is a world I left a long, long time ago. So there's going to be people in the audience with a lot more experience than me. From my experience as a very much lapsed C++ programmer, problem with operator overloading is it started off as a really nice thing. And then, yes, Dan, that's exactly it. And do anything else other than what C++ did, Dan's just typed in chat. You see, that's the point. We can look at what other languages have done and learn from their mistakes rather than repeat them. And operator overloading, well, it seems like a good idea. In C++, it kind of got out of hand. from my perspective as a very lapsed C++ programmer, there's no reason to believe it wouldn't repeat its history wouldn't repeat it with PHP. So maybe we're better off this way, where you've still got to call explicit methods, because at least that way the code should be more readable and should be more traceable. What do you think, Dan?
I'm sure he'll quickly type his response into the
I'm sure he will.
into the chat channel. Whilst he is, a quick question on the data cards. You said it can only check one thing. So if conceptually you were modeling a point on on the Earth, so using longitude and latitude, would it be valid for the data guard to take both an integer value for the latitude and longitude and validate them together? Or would that not be? Or would you have latitude and longitude as separate data guards?
Are you trying to prove their longitude and latitude, or are you trying to prove the longitude and latitude as a point that falls within your interest? What are you trying to prove?
That's a good point. Yeah. I hadn't really thought. Yeah,
I think the answer is,
if it's a point within the UK, I suppose. Yeah, let's say that.
Yeah. So I think the answer is you may first of all have longitude and latitude as types. So they would be. Sorry.
From one of the audience members, it's a trick question. The Earth is flat.
Yes, if the Earth was flat, cats would have pushed everything off the edge by now. So maybe not. I mean, this is where you get into something called type conversion, perhaps, which is probably another language feature I should have mentioned earlier with Dan's earlier question about things PHP could do with stealing. Because you might start off with longitude and latitude as two types. So first of all, you prove you've got longitude and latitude, and then you have another data guard which actually proves those longitude and latitudes fall within within the UK, for example, where you're interested in. So you ended up doing two sets of tests there. So you have data guards for longitude and latitude, and then a third data guard for your point of interest. Does that answer your question, Dave?
It does, yes. Thank you very much. Right, and we think we might have one from the audience. Can you see a way forward for the operator overloading idea to make it safe to use, but also more easily static analyzable, so your code is easy to reason about? Doesn't have to be C++ type problems.
No, I don't think that's a question from Dan. I think Dan's being inspired to see ways forward.
Oh, I see. Right.
Which is awesome.
Oh, indeed. He says, yeah, not a question. Right. I think our Q&A has done. We've got 5 questions, but they're all marked as answered. And I can only see none in the open. So thank you very much for that talk. I think everyone is clapping away behind their computers.